Welcome back to Chemical Study Zone. I am Devike Bhagwan. In this today's lecture, I will discuss about the Reynolds Transport Theorem. Okay, let's start the class. Reynolds Transport Theorem. First of all, let us consider any arbitrary system which has some mass m and volume v. As to prove Reynolds Transport Theorem, we need a system which consists of any mass and volume. So then only we can prove that Reynolds Transport Theorem exists for the system. Now let us draw CV for this system. This is known as CV, control volume. Now let us consider the system is at time t0. If we move to some time which is t0 plus delta t, at this time the system will be in this condition. 1 minute. It is our initial system, and now the system moves to some part which is in this way. This is our new system at time t0 plus delta t, and this is the system we initially considered. Okay, let us consider this. It's a CV. Initial system is nothing but the control volume. So this may be the part 1, this is the part 2, this interface, and this is the part 3. Okay, now let us consider the axis as x, y and z. Okay, before proving the Reynolds Transport Theorem, we should have to know what is n. Capital N is nothing but the total amount of mass or momentum or energy present in the system we considered. And we should also know about the term known as eta, where eta is known as the amount of an extensive property. What is extensive property? The property which depends upon the mass. Amount of extensive property by per unit mass. Here the extensive properties we considered will be this mass, momentum and energy. So this eta value for this mass, momentum, energy will be eta for mass equals to capital N by M equals to M by M, as N value for the mass is M, so it is 1, and eta for momentum equals to mv bar by M equals to v bar, and eta value for energy will be half m v square by M equals to half v square. These are the eta values for mass, momentum and energy. We should have to need them, we should know them. As from this equation, as eta equals to N by M for smaller values of M, we can write it as eta equals to dn by dm. This implies dn equals to eta into dm. Now for integrating it, we'll get the capital N of the system equals to integral of eta into as mass equals to density into volume. We can write it as eta into rho into dv. It is for the system. Okay, this is our main equation. Let us keep it apart. Now we know that the first law of differentiation, according to the first law of differentiation, the first derivative of a term and considering the differentiation of the system with respect to the time equals to limit delta t tends to 0 eta of system at t naught plus delta t minus eta of system at t naught by delta t will give us the difference of the system at how much rate does the system is moving per unit time. At the initial time t naught, the system is at this part, and for the time t naught plus delta t it moves to this part. So at what rate is the system is changing on, that we are finding out now. So we can write it as, now I will draw the same figure over here for a simple calculation. It's a CV, first, second and third. It is at t naught plus delta t. System is moving to velocity. Okay, now let's solve this equation. This implies dn of system by dt equals to limit delta t tends to 0. Here n of system at t naught plus delta t can be written as n2 plus n3 at t naught plus delta t, and again the system at the n of system at t naught can be written as n of cv at t naught by delta t. As at t naught plus delta t the system is in this yellow color, that means this interface 2 and this interface 3 will combinedly gives us the system at t naught plus delta t, and for the system as t naught, which is nothing but a cv for the initial condition we considered. So I wrote that over here. Now let's solve this equation. dn of system by dt equals to limit delta t tends to 0. Now this n of 2 can be written as this n of cv minus this initial condition 1, cv minus n of initial 1 plus n of 3 at t naught plus delta t minus n of cv at t naught by delta t. Now here we have ncv and ncv. I will take these two terms as together at single term plus dn of system by delta by dt equals to limit delta t tends to 0 n of cv at t naught plus delta t minus n of cv at t naught by delta t plus limit delta t tends to 0 n of 3 at t naught plus delta t by delta t minus limit delta t tends to 0 n of 1 at t naught plus delta t by delta t. Okay, now by the first law of differentiation we can say this term is equals to dou by dou t of ncv. Now let us solve n of t naught plus delta t and n of 1 of t naught plus delta t and substitute in this equation. Let us consider this as equation 1. Now let's solve the equation of limit delta t tends to 0 n of 3 at t naught plus delta t by delta t. Okay, as we have proved the equation that eta of any system is equals to integral of eta into rho into dv. Now I can write it as for the differentiation dn of 3 equals to t naught plus delta t. Differentiation of this term will give us eta into rho into dv at t naught plus delta t. Now if we consider this 3 of a system, now I will draw this interface 3 over here. This is an interface and now it has a area dA bar and it's moving with a velocity v bar, the system 3. So we can write the volume as dv equals to v into dA bar, v bar dot dA bar into delta t. Now I'll substitute this value in this equation. We will get dn3 at t naught plus delta t equals to eta into rho into v bar dot dA bar into delta t. Now apply limit delta t tends to 0 and 3 at t naught plus delta t by delta t equals to limit delta t tends to 0 1 by delta t, common integral of control surface. So as we are considering our separate systems like 1, 2 and 3, so we will consider this as terms as control surface systems. So the integration of control surface 3 will be dn3 at t naught plus delta t will give us limit delta t tends to 0 1 by delta t integral of eta into rho into v bar dot dA bar into delta t. This term and this term will cancel over here and we left with only limit delta t, sorry, as there is no delta t, it is simply equals to the t naught plus delta t by delta t equals to integral of control surface 3 eta into rho into v bar dot dA bar. This is the value of limit n3 of t naught plus delta t by delta t. Sorry, there is no delta t over here. And now similarly for limit delta t tends to 0 for n1 at t naught plus delta t, sorry, delta t exists, equals to the minus integral of control surface 1 plus eta into rho v bar dot dA bar. I will substitute this equation 2, 3 in equation 1, which is just this equation. As we know this term as dou by dou t of NCV. Now we got all the terms, and now let's substitute in the equation 1. Then we will get dns of a system by dt at t naught equals to dou by dou t of NCV plus integral of control surface hello guys, sorry, here we will get the term minus after solving. Now we'll get this at surface 3 eta into rho of v bar into dA bar minus integral of surface 1 eta into rho v bar dot dA bar. As you know that the n of a system equals to integral of eta into rho into dV. In place of NCV I can write it as dou by dou t of integral of control volume at control volume eta into rho into dV bar plus, now here this control surface 3 and control surface 1 will be the total system 1. We have the total control surface as eta into rho into dV bar, which is nothing but a derivative of the system with respect to the time. This is a Reynolds Transport Theorem, RTT in shortcut. Okay guys, here I'll explain each term over here. Here dn system by dt is known as rate of change of any extensive property present in system. Property present in the system, that means the mass, momentum and energy. And here this dou by dou t of integral CV eta rho into d bar is known as the rate of change of CV, that means change of control volume with respect to time. And this term integral of control surface eta into rho into v bar dot dA bar is flux quantity moving in or out of CV through its CS, the control surface. Okay, these are the terms, and this is the main equation of the Reynolds Transport Theorem. From this equation we derived the integral balances and differential balances of the mass, momentum and energy. Okay guys, this is for today. And one more notification, if you are interested in the Hollywood music of just only vocal cords or only just guitars music and all that, I'll recommend you a channel of my friend. Is just giving the Hollywood music of the only vocals and only especially the sounds. Okay, I'll just give the link in the description, you can watch that.